treat that as a rejection because I can't take the confidence acceptance.
Okay, let's settle in. We're about to start.
Yeah, use this mic. Oh, you need to use the mic.
Okay, so as a quick reminder, the sessions are being recorded, so please, if you have a question, try walk up to the mic and then ask it, and then the speakers are also encouraged to stand behind the podium and make the presentation. So, okay, so for our first talk, we have James Fairbanks from Georgia Tech about Semantics.jl. I guess when he gets here, he tells us what happened to Christine.
So Christine is here in the audience with us. So I'll be talking about the package we've been working on together called SemanticModels.jl. And it's not just another modeling framework. So our overarching goal is to teach computers to do science in an automated reasoning kind of way. And in order to do that, we have to teach them to understand science. And that's why we're attacking modeling and modeling frameworks. You can check us out on GitHub, SemanticModels.jl. Great. So scientists do a lot of things, but one thing they do most often is make models. They make computational models, they make mathematical models, they make simulations. And the first thing they do always is write down a mathematical description of the system they're studying. I like to think of that as modeling on the whiteboard. Right? You just write some math down and that's your system. But then they need to turn them into code. And that can take a long time. Julia makes it a lot easier because we have high-level programming and it's great to be working in Julia. But that still leaves them with the problem of if they change the system they're studying, they have to change the math, which means they have to change the code. That's time-consuming and error-prone. So people write modeling frameworks to make this easier. So there are all these modeling frameworks out there. The one that is considered deprecated and harmful, MATLAB and SciPy. Mathematica, Stan, which is, for each of these, there are many more like them. So Bayesian programming, Stan, JUMP for optimization, TensorFlow for deep learning. All of these modeling frameworks have a domain, and they introduce a domain-specialized language for that type of mathematical modeling. Okay. So what is a modeling framework? It's got to be some kind of mathematical object. And what the heck is going on there? So for the purpose of this talk, we'll define it like this. You have some objects, X, Y, and Z. You could think of those as types, like int, float, whatever. And then you have models, which are going to be like functions between types. So f goes from x to y, meaning given an x, you get a y. And g goes from y to z. Given a y, you can compute a z using these models. And they have to have two properties, or two operations. I can compose them the way you compose functions. So if I have one model of a system that takes an x and makes a y, or another way of phrasing that is, it models y in terms of x, and another one that models z in terms of y, I can compose those to get a model of z in terms of x. And this works just like function composition. And then you can combine models. So if you have two systems and you put them next to each other, you get a new system that's composed of its parts. Here, so kind of F cross Y, this O times tensor product type symbol, right, is put two systems next to each other in a way that they don't interact. And these correspond to composition. So in electrical circuits, you have resistors in series, it's composition, or you can put resistors in parallel, that's combination. And you can make any circuit out of these two operations by composing and combining smaller circuits. So that's kind of true for all modeling frameworks. Those are the kinds of modeling frameworks we are working with. And then you have this other fifth property that you can execute a model. So you can take one of these models, F, evaluate it, and get a program. In this case, a Julia program, foo, that takes data of type X and produces an answer that is of type Y. Okay? So if you think of these as like mathematical functions, the O times, the product, is Cartesian product. So you just take tuples. It's kind of tupling in functions. They play nice to each other. They make a modeling framework. And these types of modeling frameworks are pervasive in science. Here's an example from probability theory of Bayesian networks. So you can always formulate a Bayesian network, like you see on the left, in something called a wiring diagram, which is a data structure that represents this composition and combination. That's the thing on the right. So any modeling framework where you have this idea of like, I can put things together in series, or I can put them together in parallel. Then you get these wiring diagrams. Okay. Here's another example of a diagram that scientists love. So this is from biology, a textbook here on ecology and evolution. It's called the Susceptible Infected Model of Disease. So a person can be a susceptible person, or they can be infected, and when they interact, susceptible people can become infected when they meet infected people. And then you can go back and kind of get over the disease and become susceptible again, like the common cold. And this diagram has a formal syntax for how to make these diagrams. And then you can attach to them a formula, a mathematical formula that describes the dynamics of the system. And there's a one-to-one correspondence between these diagrams and these formulas. Cool. So here's an example of another disease called SIR. So these are diseases where there's immunity, like chickenpox. You have susceptible people, infected people, and recovered people. These are people who've had the chickenpox but don't have it now. And then this system of differential equations is corresponding. Okay. So you might think this is a toy model when I say this is my my model of disease. And you might think it's a toy model, but it's used actively in current research. Here's a paper from 2017 about the ongoing Ebola epidemic in West Africa, where they collected data every 2 weeks as people got sick, and they plotted it and fit the SIR model to the disease. So the SIR dynamics are a pretty good proxy for what's going on in Ebola. And so even these small toy models can have a real-world impact. So I defined modeling frameworks in kind of a mathy, abstract, weird way. This might be a modeling framework you're more familiar with. It's called Differential Equations. And it's a Julia package. According to the survey, it's like the 5th most popular Julia package. So we learned that this week. So in differential equations, what you do is first you declare the system of ODEs you want to solve. And you do that by declaring a function here, SIR underscore ODE. And it's going to calculate the flux of the system. And it's going to take the current state, some parameters, and the current time. It's going to do a bunch of math. We've got some expressions in here that do the math. They correspond to the equations we showed before, right? And so you declare what problem you're going to solve. You choose some parameters. You choose initial conditions. You choose a time span. And then you're going to integrate by calling the solver. Ooh, yeah, the highlighting works. So the solution is solve of the problem. That makes sense. Kind of all the Julia community has come around a consensus that this is how we should design modeling frameworks. They have a declarative part up top and an imperative solver that solves them. Okay, here's another kind of hypothetical modeling framework for agent-based simulation, where you have some data structure that represents the states, the agents, the events that can happen, the rates at which those events happen. And then if you wanted to use the simulator, or sorry, you wanted to use that modeling framework, you'd write your model like this. You define infection. Okay, I take a susceptible person and an infected person and produce 2 infected people. Recovery, I take an infected person and turn them into a recovered person. Right? So you can kind of see how this is an agent-based model of the same system of ODEs. There's a correspondence between these 2 systems. They model the same phenomena. Okay? And so this script also has this property of being a declarative part of, there's a model, and then I call a solver. My solver here is, when I solve a model, I return the solution. It's a great modeling framework. Okay. So we think of this thing that scientists do. There's a thing from functional programming that captures this. It's called a lens. So we take code, we extract out some data structure that represents the model in that code. We transform that model, and we generate the code again. So it's going around this cycle like this. Code to model, model to a different model, model to code. Okay? And so we use these wiring diagrams like this. This is a story of infectious disease. And these wiring diagrams have this property that you describe them like a story. So a susceptible and infected person get together. They're exposed. It produces an exposed person, E, and an infected person, I. Then the exposed person progresses to being infected. And the infected person recovers, and they're recovered. And I can make this model more complex by saying, oh, and then the infected person died, and the recovered person just stayed recovered. Okay. I can make it even more complex. Now the dead rested, and the recovered person, their immunity waned. They lost their immunity, and they are susceptible again. So these wiring diagrams are a universal language for describing models. I didn't come up with them. They've existed since, like Feynman diagrams are an example in physics. And you can always convert them into these, convert them from wiring diagrams to what are called Petri Nets. This thing on the right is a Petri net. And then you can convert the Petri net into ODEs. Okay. So this is how our software works. You have some Petri net modeling framework. We do some cool stuff with types, but I don't have time to get into it. But if you want to talk about types in Julia, ask questions. Okay, so we have this modeling framework for wiring diagrams and Petri nets. But after you've got a model, you want to make changes, and you don't want to start from scratch making new, start the model from scratch. You want to be able to say, the common cold is like chickenpox, except after you're recovered, like 2 weeks after that, you can get the common cold again. You can never get chickenpox again, but you can get the common cold. But there's this period where you're not going to get the common cold 2 weeks in a row. And these are structural model changes. So I'll get here. So this is an example of turning a disease that's SIR, that's on the left, to SIRS. These are diseases that you can get over and over again. And this is a meaningful transformation to the modeler. If we just treat models as Julia functions, you can't talk about these changes, where you say these two functions are similar, except there's this little diff. How do you talk about, if I give you two Julia function objects, how can you tell me what the difference is between them? You can't. But if we store models like this, you can. Okay. And so we can go back to code. So these rewriting rules allow scientists to reason by analogy. They can say the SIR model is to the SEIR model, so this is susceptible, exposed, infected, recovered, like the SIRS model is to what? Cover this up with my hand very effectively. So this reasoning by analogy is something that scientists do all the time, but there's no mathematical way to formulate it, except for now with these rewrite rules. So semantic models combines these two things, kind of wiring diagrams as a universal syntax for models and rewrite rules for this reasoning by analogy. Okay? This is how you use it. There's a Julia package that you can use. You have to check out dev on our repo. This is hot stuff. But use the software interface where you define these rules. This is the analogy. And then you apply the analogy to a new model. But this kind of looks like a modeling framework, right? I declare some stuff, and then I call solve. So we can actually represent our model rewriting as a modeling framework. It satisfies the properties that we talked about. So that's really cool. I think that's going to give us some higher order functionality. So you make these models, and then you do CodeJen. We had a great talk this morning by Stephen Johnson on CodeJen. He warned us not to do CodeJen, but then showed us how CodeJen was awesome. Not sure how to feel about that. But so this model here, this declarative code, we CodeJen it into this imperative code as a stochastic agent-based model. But then we could also turn the same model into differential equations and use the DiffyQ framework. So that's really cool. So we have a unified framework for representing models in different ways at various levels of abstraction. From I tell you a story about the agents in the model to this Petri Net thing that deals with populations to differential equations that uses a continuous approximation of the Petri Net, which implements the story that represents my scientific idea. Okay? And so we combine two things in semantic models, kind of this extract, transform, and generate cycle on the left, this lens, and these rewriting rules for how do I describe scientific models in a way that I can reason by analogy. So what our software does. It's pretty cool. I think you guys should check it out. And I think we can build a lot of technology for modeling on it. We use these rewriting rules. Hopefully we're going to teach computers to do science in the next 6 months. Yeah, and it's built on category theory. So if you want to talk about category theory, this is where we're doing it. Great. Some open questions that I have are, how broadly can we do this? I gave you kind of these string diagrams or wiring diagrams and Petri nets and differential equations. That covers a lot of science, differential equations, right? But not everything. So how far can we generalize this? The rewriting, like how do you actually compute these things? The theory has been worked out just in the last 5 years about these rewriting systems. And it's all theoretical. There's very little computational work on these rewriting systems. So how's that going to work? And then this is just model augmentation, where that's one modeling task that scientists do. They have a model, they need a different model that's derived from the first, this augmenting the model. But they do lots of other stuff. So they do uncertainty quantification, sensitivity analysis, yeah, the other things too. So what other activities that scientists do can we formalize, like model augmentation? Okay. And then I'd like to thank my sponsor, DARPA, and my team, which includes Christine, Micah, Kuhn, and Sri. Yeah, thank you guys very much.
Okay, do you have questions? Yeah.
Hey, Marco.
Hi. I was wondering about the rewriting systems that you were talking about. You said it was worked out in the last couple of years. Is there a name for like the theoretical framework?
Yeah, so this thing is called a double pushout rewriting scheme. It's based on category theory. There are arrows that are omitted from this diagram. But both the thing on the top, double pushout rewriting.
Okay.
There's also sesqui pushout rewriting, where you're given 1.5. This is 2 pushouts, where you're given 1.5.
Oh, I see.
Sesqui.
And it's just for like replacing DAGs with
Yes.
edges and DAGs with large with
Different
more
DAGs?
graphs. Yeah.
So graph rewriting is one thing. This is the example here. So you say like loop is to single vertex as 2 vertices pointing to loop is to 2 vertices pointing to single vertex, wedge. So that's graph rewriting, and that is for DAGs. Directed graphs, they can be cyclic. Yeah, so that's probably the most well-developed area, and that theory has been around for a long time.
Okay.
But this arbitrary category thing, that's what I did. So the way I describe models is that they are morphisms in a category, monoidal category. And yeah, so there's a general, if you're in a monoidal category, you can do rewriting with double pushouts.
Cool. Thanks.
Yeah, thank you. Great. Miguel.
Hey, thanks. Cool talk. Do you have a programmatic way of turning JuliaCode into the diagrams?
Right. So that is significantly harder.
Understandably, yeah.
Yeah. So the inverse, right? A modeling framework, you can take models and make code. The inverse problem, given code, what was the model, is much harder. So the things that we support right now are basically like differential equations that came from diagrams. That's one example. Another is this hypothetical ABM framework that we wrote. We wrote it to be easy to solve the inverse problem, because we care about this here at the end. This lens thing, where I take code, I extract the model, I make a new model, I generate the new code. We care about this because it'll help make kind of Siri for scientists. So you can say, hey, I have a climate model, but what if this thing about how carbon goes into the ground was changed? Like, what if people actually start pumping carbon into the ground? So you already have a model that's implemented as code, and you want to add this feature. So that's why we want to extract out the model, transform it, and generate new code. And so there was a question in there. Oh, the extracting. So the extracting is like, it's just kind of handwritten engineering, boring software that's like, if the AST looks like this, that means there's this thing in the model, and you kind of have to just do it. So we wrote this ABM framework to figure out what are we trying to extract to. Given a code, what data structure do we want in order to be able to do these transformations? And it turns out that you want to pull it out into something like these Petri Nets or these wiring diagrams. Yeah, go ahead, Ari.
So yeah, cool talk. Thank you. So what if can you model like mechanism uncertainty? So say like I'm not sure what's going on in this part of the model, so model it with like a neural network or some sort of machine learning. algorithm?
Yeah, so model uncertainty, or mechanism uncertainty as you called it. Right, so that's kind of one of these higher order functions that takes a model as input and produces a model as output. So you want to put a distribution over these diagrams and say like, well, I know I have a disease and I know that there's susceptible, infected, and recovered, but there might be a latent exposure period that I don't know about. Or it might have progressive, is that my time? So it might have progressive stages, like stage 1, stage 2, stage 3 cancer, or something like that. And so you don't know what the Petri net is. So you can put a probability distribution over them and then solve, sample a model, solve it, and that gives you a sample over the solution space. So you can turn a distribution over model space into a distribution over solution space.
Can you express that now, or it's something that you want to?
That's something we have to write. But I think everything, all the tools we would need are in place. And it would just be about.
I think AgentBased.jl would be
Yeah.
good for that.
So that's another target. We care about probabilistic programming languages, right? They're modeling frameworks. They specify computations over distributions. And so they're in scope for next round of effort. Yeah, that's an alternative approach for exploring this model space, right? So the genetic program can use these rewrite rules as its evolutionary steps, right? The wiring diagram can be its genetic code. The rewrite rules can be its evolutionary steps. And now we have a formalism for writing genetic algorithms over models. And the technical conditions on composition and combination that I didn't explain at all, but those technical conditions are required for the diagrams to be rewritable and composable. So you got to get you can't just take arbitrary diagrams and compose them. You have to give the diagrams a formal semantics, a formal syntax. So yeah, that's what we've done. And I hope if you guys are working on a modeling framework and you want to see if it's compatible, come talk to me after in like a minute, and we'll talk about it. Thank you very much.